Alright, so now we're going to talk about the definite integral as a limit of Riemann sums. So remember that the definite integral, this, is just the area underneath the curve, and we find the delta x by doing b minus a over n. That's going to be extremely helpful. And in a series where your index, we use I for your index, that's really like your starting value. The sequence of your x values can be defined as this little equation, x equals a plus I times delta x. And remember, I is just whatever number of patterns that you're working on here. So in a sigma notation, saying that I starts at 0, that just means that you're plugging in a 0, then a 1, then a 2, then a 3, and then this is wherever you end. So if it was n, you would go, if like say n was like 5, and this is 0, you'd do 0, 1, 2, 3, and then 4, because 5 minus 1 is 4. Or here you would go 1 through 5. So that's just a quick little review of sigma notation. And so here, if we're using LRAM, obviously we would use the left values, and so that's why we start at 0 and go to n minus 1. Remember that n being the number of rectangles that we're using. And if we're using RRAM, that means we're going to do the right value. So we're going to actually start at 1 and go to n, so we're not going to include 0 there. And your very first thing, this thing that you start at, it's either 0 or 1, and that value that is your 0 or 1 is always your a value, right? So even though it's the 0 number in the pattern, it's still your a value, or it's the first number in the pattern, it's your a value. And this would actually be a plus delta x, because it's the second number in the pattern, really, if you think about it. 0 is the very, very first. You're okay. And as we've talked about in the past, right, as we put more and more rectangles in there, we eventually get to a lot more accurate measurement of the area underneath the curve. Remember, that's what this is, just area underneath the curve. And so as the limit approaches infinity of either one of these two patterns, then this actually equals the integral. It equals the area underneath the curve. And we'll talk more about this later. But for now, just know that if we put infinite numbers of rectangles in there, then yeah, we would actually get the exact area. Now I know we can't exactly just draw out infinite rectangles, but this is just theoretical for now. Okay, so all we're going to work on in this video is how to convert from sigma notation to the calculus symbols, or from the calculus symbols back to sigma notation. And so that's all we're going to really work on here. So remember, all of this hinges on this idea that x equals a plus I delta x, and then we find delta x by doing this. So let's go right to it. So we can look and we can see this pattern here. We can see that we're starting from 1 and going to n, so that's like this one. Just kind of underline it so we have it as a reference. And you can see something going on here. This is always going to be f of a plus I delta x. Remember, that's like your x value. So this is really like your height. Maybe we could even kind of put here, this is like your height, and this is your width. And so that's how you're calculating the area of all these different rectangles. So here, and your width, I remember, that's your delta x. So here is actually the delta x, it's right here. So we already know what our delta x is, so we can actually just say 4 over n equals our delta x. Okay, I'm going to leave that there for now. We're going to come back to this later. And then we're going to look at our function. And so I'm going to start with this idea that x equals a plus I to the x. And I'm going to think about this is really the x. If you think about it, this is the natural log of x. They're just defining x in a different way. So let's think about this. This is like your x. So this is like saying 1 plus 4i to the over n. This equals a plus I times delta x. Well, we can already see what our delta x is. It's 4 over n. So we can see that this is really like saying this part right here is like the delta x. And so we can actually kind of separate this all out. If you were to rewrite this, right, this is like saying 1 plus I times 4 over n. And so here's your delta x, right? Here's your I. And so that means that this is your a value, and that's going to be really important for us to analyze this function. So we know that a equals 1, and we're getting that from this information inside here. We're just reading this pattern, knowing that it's always going to fit this description, and so we're able to say that the a must be 1. That's a really big deal. So let's just put a equals 1 here. And so all I'm teaching you right now is just kind of how to read this. So there's your a value, a equals 1. Well, knowing that, we can go up to this a plus I delta x, and we know what our delta x is, and we know that b minus a over n is equal to delta x. So let's go ahead and make this little formula. We know that 4 over n is delta x, and we also know that delta x is b minus a over n. Well, these both have n's in them. In fact, if you multiply both sides by n, you would just get that 4 equals b minus a. And now we actually know what a is, so we can plug that in. You get 4 equals b minus 1, add 1 to both sides, and now we also know that b equals 5. So what we've just determined is we just determined the lower and upper limits of our integral symbol. Remember, I'm not even doing any math here. I'm not trying to calculate the area. I'm just trying to convert this to the integral notation, and then here we're going to convert back. So what does this look like? Here's my integral symbol, and I know that my lower limit was 1. We found that here because my a value is 1. And my upper limit is 5. So now I'm just going to rewrite the height and the delta x. Well, we already determined that this thing in here is just x, so this is really just ln of x. And then this is just delta x, so you could just put delta x, but when we're using calculus terms, we would put dx. And so this whole thing is just another way of saying, all this crazy notation, it's just another way of saying what is the area from 1 to 5 underneath the curve of the natural log of x. That's it. All right, now let's do it the other way. Okay, so let's do the opposite now. And we can quickly identify a couple things. We can see that this is your function, and we can see that this represents the delta x. We can see this is the a, and this is the b. And we're going to just rewrite it all so that's in sigma notation. And we're going to start with these two formulas, right? So we're going to start, we know that delta x equals b minus a over n, and we know that x equals a plus I times delta x. So let's just start plugging in what we know, see if we could simplify this out. First, let's find the delta x. We have our a and our b. They're labeled right there for us, so this should be pretty easy. It's just b is 5 minus negative 3 over n. Well, that's a double negative, so it turns into plus. So it turns out that our delta x is just simply 8 divided by n. Well, this is going to be useful here, because this is how we define our x. And we already know what a is, so x equals the a value, which we now know is negative 3, plus I times 8 over n. And we just clean this up a little bit. We would write this as negative 3 plus 8I over n. And this I is not to be confused with imaginary numbers. It's just your index in using sigma notation. Okay, so now that we've rewritten this thing, we can go ahead and start to write our sigma notation. Keep in mind, we're going to write it both ways. We're going to write LRAM and RRAM. So let's just start with the LRAM. And remember, the LRAM starts with your index at the 0 term. And now it's f of, well, x. And our x is a plus I delta x, which you determine is this. So I'm just going to say f of negative 3 plus 8i over n. And then it's times by whatever your delta x is. And we just determined that our delta x is 8 over n. All right, and this thing goes to n minus 1. And so here's the LRAM of this guy in sigma notation. And now we're just going to do the same thing for RRAM. It really is the exact same thing. The only difference is now this is going from 1 to n instead of 0 to n minus 1. So let's rewrite that. Now it's going from the index at 1 to actually n, and it's the exact same information. And so basically all this is saying is, it's just saying if you add up all the areas from the 0 term, meaning you plug a 0 in here, to the last term, meaning you plug an n, whatever number of rectangles you use, minus 1, you'd get the area of the curve, or the area underneath the curve, I mean. And that's it. So all this lesson is about converting the language back and forth, converting from sigma to integral or integral to sigma. That's it. See you guys on the next video.